Let me unfreeze the screen and let's get going. So, e to the x. Sophia, what did I say it approximately was? Do you remember?
2.17.
I think it's 2.71828. I'll double check me on that. So I guess 2.1 and 2.7. For 2.1, we'd be using 2 to approximate. For 2.7, we'd probably be using 3. Okay. So we'll be using probably like 3 or like 2.5-ish to approximate e. But does that make a huge difference when you guys went to graph e to the x? Where does every exponential function that's non-transformed, where does it cross the y-axis?
1.
For those of you guys just joining us, we're sorry that you weren't able to be at school today. We miss you. But the kids were working on an opener of graphing these 3 functions. Graphing the original e to the x, who's that? And then graphing the transformations of that function. So Sophia just reminded us that e is approximately 2.71828. E is a number that appears a lot in nature, a lot in
factorials.
Like radioactive decay, a lot in carbon-14 dating, a lot in like exponential growth and decay, like bacteria populations, all sorts of stuff. E and ln show up. You guys will see them in chemistry, you should at least. So we have 2.71828, but what we were saying is, whatever that base was, he's exponential, so he has an intercept at 0, 1. How do I know that he's growing and not decaying? Okay, then how about Okay, so since he doesn't have a negative in front, that was like Cassie's yesterday, that would flip it down, so that'd be wrong. He's a positive number, so he's not one of Emily's failing ones from yesterday. Right? So that wasn't bad.
She wrote math.
Weren't there ways that it could actually decay instead of grow? What was true then? Yeah, like 4/5, 2/3, 1/3, 1/4. All of those raised to powers would decay, but this guy's 2 point something. Like he's above 1. So we know he has to grow. Now, technically, how is he going to grow? Well, first of all, he grows, he increases from the left very, very slowly. Basically, it takes negative infinity to 0 for him just to get up to 1. But then once he hits the axis, once he hits x equals 0, then he starts taking off. Well, kind of taking off. Do you guys realize every exponential function technically has 2 important points?
Mm-hmm.
One important point is the y-intercept. The other important point is the x-intercept. No. Remember, Alec? What does it never do? Okay, so it's not the x-intercept. So what's his other important point? At 0, anything to the 0 power is?
0. 1.
1. But what's anything to the 1 power?
Itself.
Oh, so every exponential function has 2 important points. One is all of them are going through the point 0, 1, but the other important point is all of them are going through the point 1 and themselves. So 1 and themselves, wouldn't that throw E around 2.71828-ish? Aha. Now, where would 2 to the x have been? Down here at 2. Where would 3 to the x have been? Up here at 3. Where would 10 to the x be? Up here. So some of them increase quicker than others. Some of them increase slower than others. All right. There we go. Does he have a vertical asymptote, or is he just going really steep, really fast?
Really steep, really fast.
Yeah, because if I plug in 2, it works. 3, it works. 10, it works. 1,000,000, it works. There is no vertical asymptote that you plug in, it doesn't work. It's just going real steep, real fast.
Really steep?
Yeah.
If it kept going, wouldn't it eventually hit 0?
Well, practically speaking, can we show it getting closer to 0 forever? So I put the arrow. But if we zoomed in to where the pixels weren't stopping it, like a calculator would stop it and just cut it off. If we kept zooming to where the calculator had space to show it, it would never hit.
So then, like, would there be a starting point then? Because doesn't it have to hit 0 at one point? So where does it start?
But it is going to be 0.0000000000000.
So it's just infinitely small.
Which practically would be 0. Because how many things in nature or in life can actually measure to 0.0000? And there's this thing called Zeno's paradox. Technically chapter 10, 11.
Is it big brain stuff?
No, not 11, 10, 9. Maybe chapter 9. Sequences and series. Hey, you guys are taking the PSAT tomorrow. Might you see a summation?
Yeah.
Ooh. What?
Ooh, can you guys open your graphing calculators that you're allowed to have at your PSAT tomorrow? Don't forget it. Open your graphing calculators. Can you hit the math button? And can you go find me in the math menu something that looks like a big old E?
Yeah.
And maybe you can't find the big old E. Maybe it's actually the word summation. SUMMATION. Where is it? Math under the first thing and hit it. Hit enter. Is there a big old E that shows up?
It looks like a beta.
Okay. The big old E. This is chapter 9.
It's the thing you see at like at fraternities.
Yeah, it's a sigma. And sigma is usually a Greek letter that's used in like fraternity abbreviation, whatever weirdness. With sigmas, before I talk about Zeno's paradox, because Zeno's paradox is from the sigma chapter, a lot of kids, once they get there, is like, oh, that was on the PSAT. Why don't I show you the day before the PSAT?
Oh my.
How do you do something like?
Oh my god.
Oh, I remember this. Get out of here. No.
Just in case you see it tomorrow. Just in case you see it tomorrow. I'm helping. Has nothing to do with what we're doing right now.
I'm getting PTSD of Mr.
Where did the 5 come from?
No. This is what you're given. This is what you're given. How would you do it?
Mr. G.
Plug it into your calculator.
I don't want to think
You
about
can
that.
plug it into your calculator. Literally. If you're allowed to use your calculator, you can put a 1 down here. You can put a 5 up here. You can actually change whatever letter they give you to be an X, because there's an X button that's really easy to use. You can do that. If they give you an I or an N or a K or a C or anything weird, you can actually have the calculator do it. Or you could do it, well, the old-fashioned way, which says, start at the bottom number and plug it in, plug it in. And then plug in the next number. Plug it in, plug it in. And then plug in the next number. Plug it in, plug it in. And then plug in the next number. Plug it in, plug it in.
I'm definitely using the calculator.
And then plug in the next number. Plug it in, plug it in. Woo! I'm saying right again. How many times did I plug it in, plug it in?
5.
Why?
I
I started plugging in at 1 and I counted up by 1, plugging in up until 5. Hey, what if you see something tomorrow that has a 8?
8 times 7 times 6 times 12 times 4.
Or math button to save you time, go over to for probability. It's going to show up in chapter 8.
Oh, okay, 5.
But there's a factorial is what it's called, an exclamation point that might save you time.
The 5 above the sigma, does it signify how many times you have to plug in a number?
No,
What
it tells you
number
where to
is
stop.
So the last
So,
number you plug in should be that
If
one.
this was 3 to 5,
Yeah.
I would have
Print this.
started there.
Oh.
Does that make sense?
easier.
Sometimes there are formulas and sometimes there aren't, depending on the type of sigma that's given.
So I'm gonna click on this one.
So use either the sigma in your calculator or plug it in. Okay, anyway, Zeno's paradox. It has to do with the sigma section, which has to do with summations. You're adding together different things. But basically, long story short, Zeno's paradox says, if I want to get from here to the stool, and I have to, every time I take a step, cover half the distance remaining. So we could talk about me to the stool right now is one arbitrary unit, one random, I don't even know.
One juju.
You're welcome. Okay, so one arbitrary unit. I am going to, with my first step, cover half the distance. Okay? So, how far have I gone?
Half of this.
Half, right? How far have I gone now? 3/4. Right? Because it's a half plus a fourth. How far have I gone now? A half plus a fourth plus an 8. And then a half plus a fourth plus an 8 plus a 16. And then a half plus a fourth plus an 8 plus a 16 plus a 1/32. Mathematically, how long will this problem continue?
Infinity.
Forever. Because you can keep on cutting in half, cutting in half, cutting in half, cutting in half forever. But eventually, what limits me in actually being able to take infinitely steps?
Your destination.
My destination is limiting me, that's true. But what's limiting me from being able to take the infinite steps towards my destination? Because mathematically, there are infinite steps. My feet. Right? Because right about now, right about now, my steps don't really mean anything. Because what's true? I'm here. So practically speaking, math sometimes modeled in a way that's more ideal than practical. But the ideal, that's a rough way of saying it, but it's okay. It has practical implications despite its idealistic foundation. There you go. Anyway, coming back. So, Emily, practically speaking, it gets close enough to 0 that we basically would call it 0. However, mathematically speaking, it never hits. Does that make sense? Where are we at? We're supposed to be graphing transfer functions. You guys getting me off on Dino's paradox and your PSAT. So, what are the transformations? I know, it was me. What are the transformations in letter G? Up 3, reflection in the y-axis. Good, because it's an inside negative, and that means it's going to be a horizontal flip. So long story short, horizontal flip, then wait a minute. Does this get a little tricky?
Yes.
I mean, I have a point. Can I take that point up 1, 2, and 3?
Mm-hmm.
Okay, that's nice. And I have a second point. I can take him up. Well, that'd be 3.7ish and 4.7ish and 5.7ish. I can take him up 3.
Move it around. You gotta move it around.
Oh yeah, because there's a reflection. Okay. So I can just flip him over here to -1, right?
Mm-hmm.
Okay. Got it. But now what?
You need to make the asymptote.
Good. Because if you try to decay, if you try to swoop, which you would have to do the other way, right? Would some of you end up making it wrong?
Yes.
That's not right. It's supposed to be a horizontal asymptote. So when you shift an exponential graph, you have to shift, I would say, 2 points. Those 2 key points. Remember parent functions? Back in the day, we would have a few key points that we would move around, right? Shift the key points, but don't just shift that. What else did this e to the x technically have that we didn't graph? What's going to happen to him? Up, 1, 2, and... So check it. Life gets a lot easier because you're like, oh, hey, got it. There it is. Got it. So just shift your points, shift your asymptotes. That is a key feature as well. Does that make sense? Okay, so we had what? We had a vertical shift up 3 and a reflection. Oops, I can't spell reflection, but that's okay. Reflection in the y-axis. Okay, what was going on in green? I like the up 1, I like the left 2, but what else do we have that we have to be careful of? Okay, so which one do we do first? Do we go up 1, left 2, and then reflect so we end down? Or do we reflect and then up 1, left 2, and end up? Do you guys see the dilemma? This is one where order matters. Some of you have hypotheses, but one of them is, Alex, focus, one of them is going to land us with it being up, and one of them is going to land us with it being down. Those are 2 totally different graphs. So even if you're like, no, I know which way it's supposed to go, how could you be safe and double check? No, without your calculator or calculator or calculator.
I don't know calculator. Oh, that's funny. Calculatrice and
I really
fresh.
thought you said Dora.
Anyway, coming back. What can we do? Yeah, tell me about it. I'll be in French and Spanish for calculator. I mean, that's better than some. Okay, so couldn't I always just start plugging in stuff?
Yeah.
Why am I going to start at -2?
Because
It's easy. Because -2 plus 2 is 0, and 1 minus e to the 0. 1 minus e to the 0 is just 1 minus 1. Anything to the 0 power is 1.
Four.
Oh dear, half of us still said 0. Anything to the 0 power is
1. Boomers.
1 comes out of anything to the
0?
Itself. Wait, what?
Just kidding, come back. So if I have this point, what does that mean? Can't I go right now, -2, 0?
Yeah.
Okay, well, which one lands me there?
The first one.
I see my left 2. I see my...
1, 0.
I think it flips. Do you guys see it? I think it flips. goes up 1, left 2. True? See it? So I'm going to go ahead and do my reflection in the x. I'm going to do my up 1 and my left 2. If you guys didn't see it with 1 point, what could you have done? Yeah, you could have done another point. And then you would have had 1 minus e to the 1, which you're like, I don't know what that is, but wait, didn't we say e is about 2.7-ish? So can't I say negative 1.7-ish? So I could have gone negative 1 and negative 1.7-ish, and been like, oh, he's swooping down. 1 minus 2.7-ish is negative 1.7-ish. Check it, do it in your calculator. I think you might be able to see it. So sorry, what am I doing? Oh, I'm reflecting up 1, left 2. I'm reflecting 1, 2, 3-ish. I'm reflecting up 1, left 2. Oh, I see it. Wait, where's my horizontal asymptote though? 1. Nice. Good eye. And then swoop, there he is. Is that a vertical asymptote? No, he's just going very steep, very fast. How'd we do? That makes sense. And that can get you kind of tripped up because then you might go too low or you might not know how to swoop it. Remember the asymptotes. And also, if the order matters, just work it out in your head. If you're not totally sure, just make sure. Make a table. Do a couple points. It should either match up with what you're doing or what you think it is, or it'll be completely opposite, and the order should have been different. Okay. Bloop, bloop. Wrong way. Sorry. What we didn't get to see yesterday, where is he? He's here somewhere. Ah, here he is. What we didn't get to see yesterday is the one-to-one property of exponential functions. The one-to-one property of exponential functions. Do you guys remember that we talked about one-to-one when dealing with, we have done this issue. Yeah, inverse functions. Switch x and y, solve for y, f inverse of x equals, remember? 1-to-1 was a function that passed the horizontal asymptote. 1-to-1 functions say each x has a unique y, each y has a unique x, which means there's only one way that this could be true. Basically, the function is not 1-to-1. There's more than one way for that to be true, so we wouldn't be able to make this statement. However, exponential functions, since they pass the horizontal line test, will have unique solutions. There's only one way that one exponential could equal another exponential if their bases match. There's only one way that can be true. Sophia, what were you saying?
If the exponents match.
The only way two exponential expressions can be equivalent if they have the same base as if their exponents are equivalent. Which is really nice because in something like the first one, I can say, oh, therefore x has to equal 3. Sorry, it did take me like 10 seconds to do the mental math. But x has to be 3. How did I get that? No division. This is 2 to the power of. If I divide by 2, all you have to say is 2 to the 2x minus 1.
Wait.
Oh, when I divide, I'm allowed to divide if you really want to, but you just made it worse. When you divide, you subtract exponents out.
Where did the negative 1 come from?
Well, it wasn't there a second ago, but Sophia said she wanted to divide by 2, and division with like bases allows you or makes you subtract exponents. I can't cancel out a base. I can just change the exponent. And I'm not sure that really helped, but I was trying to show what division would do. Now, could we keep dividing? Because then the 32 would become a 16, the 16 would become an 8, the 8 would become a 4, the 4 would become a 2, and the 2 would become a 1. Hey, 2 goes into this!
Yeah.
How many times?
8?
It goes in 32 times, but how many times, like with an exponent? Because doesn't 64 mean 8 and 8? And doesn't 8 and 8 mean 2 and 4 and 2 and 4? And doesn't 4 mean 2 and 2? What is 64 the same thing as?
2 times 2 times 2 times 2 times 2.
Yeah, aka 2 to the power of 6. How did I get 3? I said, oh, look, the bases match, and their exponents have to be the same. So therefore, I'm not canceling the bases. That's technically mathematically incorrect and illegal. But I am using the one-to-one property to be like, that's only possible, that's only true if the exponents equal. Does that make sense? So ready, set? Go find the x. Oh, but it's in the denominator. Oh, but denominators can be written as numerators if the exponent is changed to be
negative.
All you cute kids with your calculators. I mean, that's cool and all. The problem is you probably couldn't use it.
Boomers.
No, it wasn't like a. I wasn't adding them. I was just informing. Warning. Challenge. Talking to groups. Some of you, your brains are like, yeah, got it. Some of you are like, I don't even know where to start. Talk
I think I'm actually doing this line right now.
Jaden's gone, so anyone wants to adopt Ella and Megan, so she's kind of sitting there. But they're not gonna check in with them when you guys have my 2 groups of 2 can powwow.
Big brain hours.
Does your group agree? You guys good?
Sorry. What do you get, Caitlin?
So I know that x minus 2
Does the Smash Bros. When Sam Splash, she just goes like. She has the hand. I went to Fresno on Saturday and my friend was about to switch and bought extra Joy-Cons to play the Smash Bros. On the Switch with like 8 people. Not that games. So for you, that's the goes there.
Alright, so what did 1 over 125 get to be rewritten as?
5 to the power of negative 3.
Nice! And if 1 over 125 can be written as rewritten as 5 to the negative 3, and if I have 5 to the x minus 2, it's as simple as, because of the one-to-one property, haha, exponent must equal exponent, which means x must equal negative 1.
Where does it say I x equals y?
Oh, if.
Oh.
If and only if. Which, if you guys want to see the really snazzy math notation, if and only if in like mathematical proofs is written I, F, F. If. Mathematicians are lazy. If and only if. But if you ever see IFF, don't say if. If you it's gonna make fun of you. Alright. If and only if, and be like, haha.
We should like have
So, E. In our notes, E. His name is the natural number.
E.
Hey, I just told you how he shows up in nature a lot. He's the natural number. He is approximately. Oh, sorry. I don't know why. I put it blank. No, E is approximately 2.71828. And I think he starts.
This is E.
I know what. Natural number is his name.
No, like on the side it says E.
And never mind.
Eh.
That was A.
I'm reading A.
A, B, C, D, E.
Did I say A? There you go. That's why I said A.
Oh, yes,
Oh.
I said and I was like,
We should have.
Hold on, someone go check my decimal really quickly. What copies? Is it 18281 1828? Is that what it is? It starts copying somewhere in here, and I always forget where.
281.
In your calculator, if you put in E. Hey, how do you put in E? Is it a thing? Look at the ln. It's second ln. Where's the ln? Right by the log. Hey, ln has an e above it, and log has a 10 above it. I think that's like a hint as to who's who and what's what. Does it keep going?
Yes, to infinity.
Oh, and that's the right pattern? 1, 8, 2, 8, 1, 2, 8, 1, 2, 8, 1.
1, 8, 2.
1, 8, 2, 8, 1. Oh, 8, 2, 8. Thank you.
Funky monkey. Funky dog.
There you go. Okay, so what changes when you have an E? Well, guys, did the graph change a lot?
No.
We just had 0, 1, which we already knew, and then we had 1 E, and E was like an awkward in between, so E is like in between 2 and 3, right? But besides that, didn't he still have a horizontal axis at 0, and didn't he still swoop? There he is. So graphically, it's not that much different. He just has a different value for x equals 1, but so will every exponential function. No big deal. We just need to know who he is. But what do we do down here when we say solve for x and we have e's as the bases?
E.
Oh!
The same way.
Because it's still 1 to 1, right? E was still 1 to 1. So therefore, exponent has to equal exponent. So therefore, what do we have? X equals 1/3? You're having too much fun, son. But what's going on when we have this guy, and all of a sudden we have x squared plus 6 equals 5x? Subtract the 6 and square root.
Funky quadrant.
We get everything to one side, don't we? And then don't we go ahead and do a...
Oh.
I'm sure that was helpful. X minus 2 times x minus 3 is equal to 0, so therefore, x equals 2 and 3. Wait, 2 and 3, are those both legal?
Yeah.
Because the domain of any exponential function is all real numbers. Is there anything that's illegal? No. I mean in the sense of, are any x's unable to be plugged in or giving us any discontinuities? No. They're legal. It's okay. Why am I bringing up the idea of whether or not answers are legal?
Because of real zeros.
E says, I'll take all the x's, no big deal, I just can't have all the y's. Ln or log say, I'll take all the y's, but I can't have all the x's. And if it can't have all the x's, logarithms are going to have illegal answers that sometimes appear. Okay, that was the homework that was supposed to be due today, but I gave you a little bit of grace because we missed out on the one-to-one property yesterday. But we still have to go to section 3.2. Hey, I warned you it's on the board. You can complain for about 1 more second. And we're done. Okay, so here we go. Section 3.2, it's time for logs. Take the log out of your own eye before dealing with the speck in your friends.
That's a Metallica reference.
It's actually from the
Not
Bible,
that
but
Bible,
okay.
you silly goof.
It is a Metallica reference.
Well, Metallica
There are a lot of pop culture things that do have people with biblical backgrounds. Mumford and Sons, have you heard of those of them?
Yes.
Holy cow.
No, Metallica is biblical. The singer is a Christian, used to be a pastor. I'm not even joking.
Then why did you make it out of your church for playing it?
Because my friends started cussing.
But you don't follow after him, right?
Of course I don't. If I don't sing, I play guitar.
Okay, are we taking notes
No,
while we're
definitely
learning
not.
so many riveting facts?
Sophie is a hardcore woman. I have a baby boomer.
No.
I come from the generation.
First off, I'm not from World War II.
That's the greatest generation, smart one.
I think it's like the worst generation.
No, they did okay, but
What, the greatest generation?
not
The-
worse.
Baby, yeah, the baby boomers are the worst. That's why everyone makes fun of them. They're the worst generation. Because of Nixon.
Okay, one man didn't make it to work.
Yeah.
You know what slogan was literally a name you can trust? That was the slogan.
So we like history and politics. Good to know.
I just like memes about our presidents.
Okay.
What is it called?
But
It really is.
Whoa, so much stuff is going on. It's okay, it's catching us up. Why? Well, some of these things are already filled in, right? The weird thing is, hold on, this spacing is awkward. Because it's not log on top of x. It's not like a fraction of log of x. It's like a square root of x or a sine of x. I need an of. Or like an f of x. There we go. The spacing's better now.
Wait, do we need room between those two things?
No. Oh, you need to write who he is.
No, okay.
No. No. It was just me making it pretty. Sorry.
It's pretty regardless.
Transcendental. You're transcending.
Ah, shoot.
Jesus.
Whoa! Why did the word inverses show up?
Because they like flippy that deal.
Yeah, remember how inverses flip across the y equals x line? Oops, that didn't work out so well.
It's the same thing except for it's flipped.
Exactly, but flipped where and flipped how and flipped across what?
On y equals x.
Got him.
I'm a genius.
That's why it's an inverse. So, exponentials, swoop up. Logarithms, swoop up differently. Awkward. They both swoop up, right? You see it? They're both increasing. And how are they increasing? Where are exponential functions coming from? Exponential functions are coming from negative infinity going to positive infinity. Oh, that's right. Exponential functions have a domain of all real numbers. So where do logarithms come from?
They come from the inverse.
From y's negative infinity to positive infinity. Because inverses, don't the domains and ranges switch? So wait, that's awkward because we don't usually use y's to describe where it's coming from. So hold on, what x's is the log coming from?
Positive.
I like both. I like 0 and I like positive because it's coming from 0, but can it ever hit 0? Can
No.
No. It's going to skim its vertical asymptote the same way that exponential skimmed the horizontal. Oh, all the x's and y's switch. So if this guy had a y equals 0 asymptote, guess what this guy's going to have? An x equals 0 asymptote. But instead of being horizontal, it flipped. It's going to be vertical. So logarithms have a vertical asymptote at x equals 0 the same way that exponential functions had a horizontal asymptote at y equals 0. That makes sense? Kind of. Lots of things are flipping. However, look over here really quickly. This is only going to be perfectly true when the log and the exponential have the exact same base. This is only true when we have something like a to the x compared to or compared with log base a. If you have y equals a to the x, then y, I like f of g equals f of x equals a to the x, and g of x equals log base a of x. Now, here's the weird thing. If I'm showing a logarithm with a base, what's the dealio with the two buttons in your calculator that have no base shown? Because 2 to the x would go with log base 2, and 10 to the x would go with log base 10, and 15 to the x would go with log base 15. So who's this guy that has no base? Who does he think he is? Look at the button in your calculator, and what's the power of above him? If you were to hit second log, what would it become?
10.
10 to the x. Do you see it? Second log. If you were to look up. Remember the second's like a shift button?
Yeah.
Second log, isn't it 10 to the power of? So second log, if his inverse is 10 to the power of, his original is log base 10. Now I'm going to put that in quotes because that's not technically what we, or how we write him. Common log has a base of 10. Common log has a base of 10. Kind of like our entire number system is based on tens, right? Well, not computer programming, I I guess that's based on 2s.
But isn't that 1 0?
Binary code.
I watched a lot of Matrix.
What's going on down here?
E.
Ooh, nice. Why is it an E? Look at your calculator. What happens if you hit second ln? It's E to the power of. That's a nice little calculator telling you the answer. So ln is really just a log, and log is just a log, and logarithms are logs. Yes, 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 yes. Ooh, ooh! Wait, that's getting too intense. Hold on, slow down. Wow. Why are these notes saved? It helped on the first page. The same way that we identified the key pieces of an exponential, we need to identify the key pieces of a logarithmic. Hey, look at the front board. That's right. We're doing exponential and logarithmic, like all chapter long. We talked about the word exponential yesterday with just a couple things, and then we're talking about the word logarithmic today with just a couple things.
Log base of 8x.
I think the book shows A. To be honest, I totally like B a lot better. B for base. It's a lot more fun, but it doesn't really matter. Remember, they're just using a variable. They're just using some sort of variable to signify a constant. It could be log base 2, log base 7, log base 5, log base 2.71828182818281. Oh, that's right, that's E. Log base 10. Oh, that's a common log. So when you're ready, go prove to me you know how to use the log button in your calculator.
Wait, but the log button is log base 10. Oh, ln is base E.
How are you supposed to do a log base 2 or a log base 4 if you can't use either one of those buttons?
Well, you can.
There technically is a formula where you can use both of those buttons.
Log
However,
base.
we haven't talked about the formula yet. Is there some place else in your calculator that has a log base 2 or has a log base 4?
Yes.
Math.
Math. Got him. Doesn't it literally say log base?
Yeah.
Somewhere.
I found it.
I think you have to scroll down, 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 down.
Yeah.
Math, down, 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 down. There's a log base.
Live.
There's a log base. Now, sadly, I did hear Alex say the answer, but I might not have necessarily known the answer and whether or not it was right. However, I totally agree with his 5. And guess what the second one is? It's 1/2. But I haven't looked at these notes since last year. Question, how did I know 5 and 1/2 without plugging it into my calculator?
You're just dividing.
Wait. What? How did I? Why did I? Emily said it's 2 to the 5th. What was she talking about? I wrote it and I agree with her, but how did she get 2 to the 5th? 32 is 2 to the 5th power, so you can rewrite 32 as 2 to the 5th. That's interesting. That ends up being 5, but how on earth did I get 4 to the 1/2 that ends up being 1/2? I thought we were plugging in 2. And how on earth is 2 related to 4?
It's square root.
Plugging in 2 can be written as a square root of 4. Well, why would, sorry, that's a 4. Why would you rewrite 2 as the square root of 4? If I can make the bases match. Wait a minute, so is every logarithm? Alex, hold on, this is important. It's the one thing that Miss Silvo remembers from her high school training.
Oh my goodness.
Above algebra 1. Literally, you can ask her. It's the one thing she remembers from her high school math, besides like basic algebra. else you got? Oh, that's from basic algebra. That's algebra. From her advanced math. Logarithms are powers. Logarithms are powers. Technically, a better way of saying it in today's terminology, logarithms are exponents.
Knowledge is power.
Sure. Logarithms are exponents. Kind of trippy. So whenever you have a log of an expression, when you plug it into your calculator, when you add a number, you're saying whoever is in here is this exponent of 2. Which, if we can make the bases match, man, our lives are going to be nice and easy and simple. If we can't, well, it's a little tricky. Don't worry, we're building our toolbox. We're building our rules that we can solve our puzzles with. I'll see you guys later. 3-1, have it done by Thursday. 3-2, if I were you, I'd start. Adios, au revoir, I'll be your soon.